I want to start today by asking you to visualize the absolute edge of our knowledge. And I don't mean the edge of the map or the edge of the solar system. I mean the point where physics, as we know it, just kind of throws up its hands and quits. Imagine you were falling into the deepest gravity well in the universe. You're crossing the event horizon of a black hole.
It is the ultimate mystery, right?
No.
The point of no return.
Right. And if you ask a standard physicist what is actually down there, what happens to all that stuff that gets sucked in, they usually mumble something about a singularity. And if you push them on what that actually means, they say infinite density. Which, let's be honest, sounds really impressive, but it's really just a fancy way of saying the math broke and we have absolutely no idea what's going on.
That is essentially correct, yeah. In the world of physics, infinity is usually an error message.
An error message.
Exactly. It's a sign that the theory has failed. It's a placeholder for a mechanism we just don't understand yet. When general relativity tries to describe that tiny point, it crashes.
Well, today we are going to try and fix the math. Or rather, we're going to look at a brand new paper that claims to fix it. And let me tell you, if this researcher is right, the universe is not at all what we think it is.
It's definitely a radical shift in perspective. The document we are doing a deep dive into today is a theoretical paper. It's dated February 15th, 2026. And it's titled The Infinite Descent, a fractal model of cosmological singularity and subatomic cell similarity. It was written by a researcher named Enkamgalan Nussen-Jargal.
The Infinite Descent, that sounds like a heavy metal album, but it's actually about geometry. So the mission for our deep dive today is to unpack this theory. A theory that claims the universe isn't just big, it's an infinite set of nesting dolls, like those Russian Matryoshka dolls, but all the way down and all the way up.
Precisely. The core mission of this source material is to solve what's known as the crisis of scale. We have this massive glaring problem in physics where general relativity, which explains gravity and stars and galaxy, the big stuff, it utterly refuses to play nice with quantum mechanics, which explains atoms and the really small stuff.
They're sort of like the oil and water of science.
Exactly. They work perfectly in their own corners. You use Einstein for the stars and you use quantum mechanics for your smartphone. But if you try to combine them like at the center of a black hole, where you have a massive amount of stuff crushed into a tiny space, the equations just fall apart. They yield total nonsense.
And this paper comes along and says, I can fix that.
It does. And the hook here, the thing that's really going to melt your brain a little bit, is the paper's central premise. The author argues that the Big Bang wasn't a one-time event that happened 13.8 billion years ago. And the speed of light, it might not actually be the ultimate speed limit we think it is.
Okay, let's unpack this, because usually when we hear about unifying physics, it involves, 20 dimensions and string theory that literally no one can visualize.
Yeah.
But Nussen-Jargal seems obsessed with something much simpler, a shape.
The sphere.
The sphere? Why is this paper so obsessed with spheres?
Well, it starts with that crisis of scale we just mentioned, the friction between the macro and the micro. Nussen-Jargal argues that nature avoids the singularity, that infinite destruction point, by using a specific geometric limit. He points out that the sphere is the form of minimal potential energy. It is the single most efficient shape in the universe.
Which makes sense. You look at a planet, right? It's a sphere because gravity pulls everything equally to the center. You look at a bubble, and it's a sphere because of surface tension.
Precisely. Nature is inherently lazy. It wants the most volume for the least amount of surface area. But here's the nuance the paper introduces. It argues that these aren't just similar shapes by coincidence. It claims they are functional equivalents.
Functional equivalents. So wait, a planet is doing the exact same job as an atom.
In a way, yes. Think about it. A planet is a sphere of rock held together by gravity. An atom is a sphere of probability held together by electromagnetism. The forces doing the holding are different, but the topology, the structural geometry, is identical.
Okay, so nature just likes to reuse code. It has one really good design and just scales it up and down.
Exactly. But the paper goes even further. It hypothesizes that the universe itself is a spherical entity. And just like an atom is inside a larger structure, our universe is contained within a larger, higher dimensional structure.
And this brings us to the topological threshold. That's a phrase the author uses heavily. It sounds like the entrance to an exclusive sci-fi club.
It's a crucial concept to grasp here. The sphere isn't just a shape, it's a boundary between scales. It's the wall between our reality and the reality above us or below us. It's a container.
So if the universe is a sphere and atoms are spheres, the obvious question is what happens when you crush a sphere too hard? Like what actually happens when matter collapses?
And this is where we get to the really juicy part of the paper, fractal cosmological collapse.
Which again sounds like a fantastic band name, by the way.
It really does. The paper asks us the question, what actually happens when a massive star collapses into a black hole? Because standard physics says it just keeps crushing down until it hits that zero-dimensional point of infinite density.
Right, the singularity, the math broke point we talked about at the top.
Exactly. But Jargel introduces this concept of criticality. He argues that matter doesn't just crush into nothingness. Matter cannot be destroyed. It can only change state. So when it reaches a critical density, it undergoes a phase transition.
A phase transition, so like water turning into steam.
Or more accurately, like a geometric inversion. The paper details what happens at the Schwarzschild radius, that's the event horizon, the point of no return around a black hole. We usually think of that as the end of the line, the drain at the bottom of the bathtub.
Right, nothing escapes. It's a one-way trip to oblivion.
But this model suggests something entirely different. It says that instead of an end, the event horizon becomes the cosmic boundary of a new universe.
Okay, wait, I want to make sure I'm really getting this. The paper is saying that when a black hole forms in our universe on the other side of that crush, it's inflating a new bubble.
That is exactly it. That is the inversion. Imagine you are pushing a balloon through a tight ring. Eventually, it snaps through and expands on the other side. The crushing gravity in our universe acts as the explosive force, the Big Bang, essentially for the universe, created inside that black hole.
That is the ultimate punchline. A black hole here is a Big Bang there.
Yes. And if you follow that logic all the way through, it implies infinite regression.
Which means?
It means it goes on forever.
Yeah.
It suggests that our entire universe, everything we see, every galaxy and star, is likely just the interior of a subatomic particle in a much, much larger cosmos.
And conversely?
Conversely, the subatomic particles we study every day, the protons we smash together in the Large Hadron Collider, they might contain universe-sized complexity within them.
That is legitimately terrifying. I mean, the scope of that is paralyzing. We're walking around with universes in our fingernails, and we are just a speck of dust in a giant's fingernail.
It redefines our place in things, certainly. It moves us from being the center of observation to just being one link in an infinite chain. It neatly solves the "where did the Big Bang come from?" question by simply saying it came from the scale above us.
But wait, if we are just a tiny particle in a giant universe, and there are tiny universes inside our particles, the physics has to change, right? I mean, I can pick up a coffee mug. Gravity's pretty weak here. But the strong nuclear force holding the atoms of that mug together is incredibly strong. If they're the same thing, just at different scales, why are the strengths so wildly different?
And that is the next pillar of the paper, the physics of the small. The author introduces a mathematical relationship called the law of inverse potential.
Inverse meaning opposite.
Yes. The formula given in the text is that energy density is inversely proportional to radius, written out as 1 over r to the power of n.
Okay, lay off the algebra for just a second. What does that actually mean in plain English for you and me?
It simply means the smaller you get, the more concentrated the energy becomes.
And why does that matter?
It explains exactly why atomic forces are so much stronger than gravity. Gravity operates on large scales, big radius, low energy density. The strong force operates on tiny scales, tiny radius, massive energy density.
So small equals strong.
Precisely. Think of a figure skater spinning on the ice. When they pull their arms in, when they reduce their radius, they spin much faster. The energy concentrates. The paper argues that the whole purpose of collapse, the reason black holes form at all, is not destruction. It is a fundamental mechanism for concentrating energy. The universe needs to crush things down to create the immense density required to birth a new universe.
Oh, it's like a compressor. You have to pressurize the gas to make the engine run.
That's a very good analogy. And this leads to a highly specific model of what the singularity actually looks like. The paper calls it the granular sphere model.
Granular, like grains of sand.
Yes. It challenges the classic idea of a point singularity,
Yeah.
a single, smooth, infinitely dense dot. Instead, it suggests the singularity is a container completely packed with high-density microscopic spheres.
Now imagine a bag of marbles, but the bag is the size of a pinhead, and the marbles are whole universes.
Essentially, yes. And because of that law of inverse potential, we discussed that those internal spheres are incredibly energetic. They are vibrating, bouncing, pushing against each other. This creates a state of dynamic equilibrium.
Dynamic meaning moving.
Yes, it's not a static dead graveyard down there. It's buzzing.
Hmm.
The paper explains that as these internal spheres get smaller, their internal pressure increases. Eventually, that internal pressure exceeds the gravitational hold of the black hole itself.
So P internal is greater than E gravity.
Exactly. And when the pressure beats the gravity, what
So
happens?
stuff blows out.
Stuff escapes. This, the author argues brilliantly, explains particle emission. We see things like Hawking radiation coming off black holes. Standard physics says it's quantum fluctuation particles just randomly popping into existence at the edge. But this paper says, no, that's a pressure release valve. High-energy spheres are escaping the crush because they're simply too energetic to be held down anymore.
That actually makes black holes feel much more mechanical, like a literal pressure cooker that's hissing a little bit of steam to stop from exploding.
It completely removes the magic of a singularity and replaces it with mechanics, pressure, and containment. It grounds the theory in something we can physically understand.
Okay, so we've got nested universes and we've got cosmic pressure cookers, but you mentioned something at the very start of the deep dive that I think is going to be super controversial. The speed limit.
Ah, yes.
Yeah.
The speed of light.
Einstein was pretty clear on this one. Nothing goes faster.
Hmm.
Speed limit 186,000 miles per second. Do not pass go. If this paper messes with Einstein, it better have a really good reason.
Well, Jargel politely disagrees with the absolute nature of it, or rather he contextualizes it. The paper proposes that CGNU is really just the viscosity of space-time at our specific scale.
Viscosity, like trying to run through water versus running through air.
Exactly. At our macroscopic scale, space-time has a certain thickness or resistance. That resistance limits how fast information or matter can travel. That limit is c.
But if you change the scale...
You change the scale, you change the viscosity. The paper introduces the scale-dependent velocity limit. It argues that at subatomic scales, specifically smaller than 10 to the negative 35th meters, the energy density is so high that it simply overcomes this viscosity.
So tiny things can actually go faster.
Much faster. Superluminal velocities. The paper suggests that at those microscales, particles can travel significantly faster than light.
Okay, but isn't that just straight up breaking the laws of physics?
It might be breaking the laws of our scale, but it beautifully solves a massive mystery in quantum mechanics entanglement.
Oh, right. Einstein's spooky action at a distance.
Yes. If you have two entangled particles and you change the state of one, the other responds instantly across the universe. Instantly. That has always bothered physicists immensely because it implies information traveling faster than light.
And this paper says it actually is?
The paper suggests that the information is moving through a subscale medium. It's essentially taking a shortcut through the microscopic basement of reality where the speed limit is much, much higher.
That is fascinating. So to us observing it, it looks like magic. It looks instant, but really it's just moving super fast through a completely different layer.
A different medium with entirely different rules, yes. It connects the spooky behavior of quantum mechanics back to a mechanical physical explanation. It's not magic, it's just aerodynamics at a different scale. It's like we are stuck in traffic on the surface streets, and the quantum particles are taking the hyperloop underground.
I love that visual. It makes the universe feel consistent again instead of broken. But speaking of consistency, there's one more piece of this puzzle the outline covers. Time.
Time and stability, yes.
We look at an atom, say a standard hydrogen atom. It seems pretty stable. It's been around for billions of years. It's not going anywhere. It doesn't look like it's doing any of this high energy breathing we've been talking about.
And that is the illusion of stability, according to the text. The paper rigorously argues that atoms are actually in a state of secular contraction.
Contraction, like shrinking.
Yes. Slowly shrinking over vast cosmic timescales.
But if they are constantly shrinking, why don't we notice it?
Because absolutely everything is shrinking relative to everything else at that scale. And it happens incredibly slowly. But here's the key contrast the author highlights in the paper. You have to look at the macro trends versus the micro trends.
Okay, macro trend. We know for a fact the universe is expanding.
Right. Macro trend, infinite expansion, volume increases. But the micro trend, infinite contraction,
Right.
energy density increases.
So the big gets bigger and the small gets smaller.
It creates a perfect infinite cycle. The universe is actively pulling apart in two directions. The large becomes infinitely larger, creating more space. The small becomes infinitely smaller, creating more density and complexity.
It's like a giant breathing lung, but it's stretching in both directions forever.
And that cycle ensures that the system never actually ends. There's no ultimate heat death where everything just stops and goes cold. There's just endless transformation.
Wow. So let's try to kind of wrap our heads around all this. What does this all mean for us?
If we look at the summary of findings directly from the paper, we have three main takeaways. First, spheres are boundaries. They're the literal containers for subscale realities.
The nesting dolls. Every single sphere is a wall between worlds.
Second, small is fast. Superluminal velocities do exist, but only at microscales. This perfectly explains the weirdness of quantum mechanics.
And third,
Third, infinity is real. There is no bottom. There is no top. There's no smallest particle that you can finally hold up and say this is the base of reality, and there is no largest universe that contains absolutely everything.
it's turtles all the way down.
And turtles all the way up.
That perspective shift is, honest, it's heavy. The paper mentions in the conclusion that just as a single cell in your body doesn't know it's part of a human, we are inhabitants of a subatomic particle in a cosmos of unimaginable scale.
It's a profoundly humbling thought. We spend so much time and billions of dollars looking for the God particle or the theory of everything, thinking we can wrap the universe up in a neat little box. But this theory suggests the box just keeps opening forever.
It really challenges that innate human need for an ending or a beginning. We want a start date and an expiration date. But nature might just be saying, no, I just keep going.
Exactly.
Before we go, I have to ask you, reading this material, do you have one of those lie awake at night staring at the ceiling moments? Because I definitely did.
I did, actually. And it relates directly to the collider experiments we talked about earlier.
Go on.
If the paper is right, and particles genuinely contain universe-sized complexity inside them, and if high-energy collapse is what actually births new universes, it raises a very specific, somewhat unsettling question.
Which is?
Are we inadvertently creating or perhaps fundamentally affecting entire universes every single time we run an experiment at the Large Hadron Collider? When we intentionally smash those protons together at near light speed, are we triggering literal big bangs for civilizations down in the microscale?
Oh, wow.
We think we are just looking at sensor data on a screen, but we might actually be playing God with realities we can't even see.
And the flip side of that exact coin is our own Big Bang, the birth of our entire reality, just the result of a scientist in the scale above us turning on their machine. Are we literally just data points in some giant's PhD thesis?
It's a very real possibility this paper leaves wide open.
Yeah.
Maybe our entire universe ends the second their experiment finishes.
That is fully mind-blowing. I'm going to be thinking about that all week. We are just a collider experiment for giants.
It definitely changes how you look at a simple grain of sand, doesn't it?
It really does. Well, on that deeply existential note, we are going to wrap it up. This has been a deep dive into the infinite descent. Thank you for listening. And remember, keep looking up. And maybe look down, too. There's clearly a whole lot going on down there.
Indeed. Until next time.